So while he's setting up, I'll post the links again. Okay, any questions before we get started? So Xiaoqing is going to present on the T1 intro folder. I'll post the link to find it. All right. Are you ready, Xiaoqing? You want to take it away?
Yeah, can you see my screen?
Yeah, we can see it and hear you well.
Okay, cool. Okay, then I can start. Yeah, thanks for the introduction. Yeah, I'm Xiaoqing Wang. I'm also working with Martin Uecker in the Göttingen University in Germany. So today I'm going to introduce how to use substrate constrained image reconstruction methods for inversion prepared T1 mapping in BART. So the materials presented here are based on this review paper, where you can also find more related work. So as usual, in the beginning, we need to set the tour path to BART. We also need several batch functions to show the images in the later comments. So it's very similar to the frequency modulated balanced SSP, also the phantom tool. Right. So in MRI, the quantitative T1 mapping is usually accomplished by the inversion prepared sequence. So after inversion of the magnetization, the signal will recover if we acquire images or acquire data continuously during this recovery. The signal of this curve will follow this exponential model, which is a 3-parameter model. Can be described by M steady state, M0, and R1 star. If we got these 3 parameters, we can calculate T1 by this formula. So, right. So, if the conventional methods need like a couple of inversions. So, one inversion is not enough. So, which takes a lot of time. So today I'm going to introduce how to use the substrate method to achieve single shot T1 mapping, which means we can achieve like T1 mapping within one single inversion. Right. So let's go to the simulation first. So yeah, we first want to create the simulated radio flash inversion prepared data using the phantom tool in BART. Yeah, in the beginning, we need to define a certain sequence parameters, which is TR, the number of readouts, the spokes, and the repetitions. So basically, the product of the spokes and the repetitions defines the total number of the radio spokes or the data along the inversion. So here is 700 with TR of 6 milliseconds, which is around 4 seconds or 4.2 seconds. And we have a number of coils and also the base resolution, because for radio acquisition, we always do like 2-fold oversampling. So the actual base resolution is half the readout. And then we use the trajectory tool to create the trajectory by inputting all these sequence parameters. So with X, the readout, Y, the spokes, and T, the time. And the last 3 is the centered radial good angle trajectory. For the later purpose, we have to transpose the time dimension to the 5th dimension. So 10 is supposed to be the time dimension, which is defined in BART. And we also need to scale the trajectory by half, because we have a two-fold oversampling. Yeah, we can also check the dimension of the trajectory one. We can see here in the zeroth dimension, we have 3. And in the first dimension, we have the number of readouts. And in the fifth dimension, we have the total of 10 points, which means 700 spokes here. Okay. And then we can create the phantom, the numerical case-based phantom using the phantom tool. So this is very similar to what Nick has introduced. So we here basically give certain parameters, which is the number of coils, the tubes, the case space. Here minus B means the basic function. And we also need to give the trajectory. Then we can get the basic geometry of this phantom. We can also check the dimension of the geometry phantom. So we have 384 in the first dimension and 8 in the third dimension, which is the number of coils. And the fifth dimension is the time points, the number of time points. Okay. So after the geometry basic function, we can also, so we can also create the signal basis because we use the inversion recurring flash. So we put the -f, -I in the signal comment. The other parameters is the number of repetitions, the TR. And then we have a couple of T1s and a couple of T2s for the tubes and for the waters in the second line. And yeah, so here we have 10 T1 values in the tubes and 1 T1 values in the water. So in total, we have 11 tubes. Yeah, so we need to join them together, join this water and the tubes to have a final signal basic function. We can also check the dimensions. So basically we have again the time in the fifth dimension and the number of tubes, which is 11 in the sixth dimension. Okay, so with the signals and the basic functions, we can multiply them together. So we need to give the dimension which we want to multiply. So because we have this 11 in the sixth dimension, so we need to give the 6 here as the input. And the first is the geometry, the second is the signal, and after multiplication, we get the case-based phantom with the inversion recurring prepared. Now we can check the dimension of the case-based data. So again, we have 380 in the first and 8 in the third and 700 in the fifth, which is time, which is, yeah, here is the echo dimension. Okay, so this is a noiseless phantom. We can also add some noise to this phantom to make it more realistic. This is very simple to use the BART noise tool or BART noise command. We can give some like standard deviation of this noise. So here I use -N1, but we can also use more noisy or little less noisy by changing these parameters here. Yeah, so we also need to create a ROI mask here. This is a very simple like image ROI mask we can use later. Okay, so up to now we have created the trajectory and the noisy case-based data. For peak recall, we also need to input the color sensitivities. So here, this part is to calculate the color sensitivity using the state data by Esprit. Because there's contrast and phase change in the beginning of the inversion for inversion prepared flash data. So usually we use the state data to estimate the color sensitivities. So in this part, the first part is to basically extract the data from like certain time points. So we basically use 300 spokes in the end of the inversion carry, and then yeah, and then transpose them, and then do AUFFT, do FFT, and then do the spirit calibration. This is very similar to the frequency modulated SSB part. So I will not go into detail, but we can talk a bit more later in the exercise part. Okay. So far we have created the trajectory, the data, and the current sensitivities. Now we can go to the linear substrate recursion. So the first step is to generate the dictionary. As I mentioned before, our model follows this 3-parameter exponential relaxation model. So we have 3 unknowns: M steady state, M0, and R1 star. Because M steady state and M0 are coupled, so we can fix one and vary the other one. So in this case, we fix M0 to be 1, and choose like 100 M steady states and 1000 R1 stars. This can be done using the BART signal tool. So again, we have inversion recurring flash and the number of repetitions, the TR. And here, after this -1, we have the range of the R1 star. So R1 star is from 0.005 to 5. And with 1000 in between, a number of 1000 components in between. And here is -3 to generate a number of M steady state from 0.01 to 1. And here's the dictionary. So before we perform the SVD, we need to reshape the dictionary to have all the components in 1 dimension first. So this is the least step. So we need to reshape the number of R1 star and M state to be in the same dimension. Here we put them into the 6th dimension. We can check the dimensions here. So for dictionary 1, it's 700 in the 5th dimension and 100,000 in the 6th dimension. So this is we have like 100,000 components in total, and then we squeeze it. Now we have 700 in the zeros and 100,000 in the 1st dimension. This step is just for preparation to perform SVD. Okay, I could run this part. The SVD is very slow in the binder, so I will not run it. But we can plot the SVD results and our dictionary here. So okay, also takes a bit time. But in the leftmost, we can see that a subset of the simulated dictionary. We can see the inversion recurring for different T1 values, basically, and the middle is the eigenvalue eigenvalues accumulated eigenvalues of this SVD results. We can see that the energy is highly concentrated. So only 4 or 5 components can be used to approximate the entire dictionary. And the right is the corresponding 5 temporal bases. So the 5 most dominant components in the U. Okay, so now we can since this list is highly like low rank, so we can use only a few components inside the dictionary to generate our temporal basis. So here we use four components. We first extract the first four components in U to create the basis, and then we need to manipulate this data, this basis, to have time on the 6th dimension and coefficients on the 5th dimension for our substrate regression. Yeah, so we can see that we have now the time on the 5th dimension and the number of coefficients in the 6th dimension. So this is the the dimension we need for the substrate regression. Okay, so here very similar. We need to define some reconstruction parameters. Here again, we use the same number of iterations as the previous modulated SSFP, which is 100. And we have a regularization strength of 0.0005. And yeah, so here we use a bit different regularization for these coefficients. We use the L1 wavelet regulation on the coefficient maps. So here is we have the spatial regularization on the coefficient maps, and also we have a joint sparsity because the coefficient maps is supposed to have similar contrast. So because they are in the 6th dimension, so we put the joint sparsity along the 6th dimension. And the last is the regularization strength. And most importantly, as before, we need to input the basis. So this is the basis we created before, and also this basis is used for our substrate regression. The others are very similar. So we have how to input the trajectory, the case space, and the cursor activities, and then we got the results. Yeah, so so this may also take a long time on Binder, so I already pre-computed the results in the reference. So here I just load it. Oh, okay, I didn't run the raw mask in the beginning.
I think you weren't running all of the cells interactively.
Oh, okay, sorry,
from the one that says N27. I think you need to start.
Okay.
Yeah.
Okay, maybe just a minute. Okay, now it should work. Right. Okay, so so here we already got the masked coefficients maps. So for the display, I reshaped them to to have them in a row. This can be easily done by the reshape command in BART. So let's see. Okay. Okay, now it works. So yeah, I have some part didn't wrong. Okay, so we can see the reconstructed for coefficients. We can see that from the first component, the energy is already quite low. So yeah, so this is the basically the coefficient maps we required for the inversion prepared radio flash. And as introduced before, we can also project the required coefficients to the images, and optionally we can perform pixel fitting to obtain T1 map. Here I only do the projections to get the images. In the later access part, we can perform pixel fitting to get the T1 map. Okay, so here are the representative T1 weighted images a long time. So we can see that the contrast changes according to different T1 values of each tube. Yeah, so that's for my part. If you have any questions, please feel free to ask.
Great, thank you. Any questions? So this example nicely shows how you start with a signal model, simulate the data, make a subspace, reconstruct. And in the next part, we're going to apply the same ideas, but with in vivo data. And we'll leave some of the cells empty for you to fill in. So before we do that, any general questions about any of the demos so far? Okay. All right, so I'm going to create breaks.